Okay, let's get going. And then obviously, like, feel free as we go along, ask questions, clarify things, whatever. Okay, so starting Unit 6, just kind of a little review of it, and then if there's more detailed questions. So Unit 6, thermodynamics. So the first thing, or one of the big things with it, we'll do some random smiley face questions as we go to fun. Is endo and exothermic processes, is understanding what those are by definition, and then identifying them from an experimental description or a graph. So kind of if they give you data, you should be able to be like, oh, that's endothermic or exothermic, or if they show you a graph, you should also be able to identify it. So just to remind you of our energy pathway diagram, so those are like what I think of as the roller coaster graphs. So an energy pathway diagram, that's what they're called. The y-axis is the energy. The x-axis is just like the progression. It's not usually like a strict measurement of time, but it's just saying as the reaction progresses. So it doesn't really normally have units. But these are the graphs that look something like this. Or they can have more, they can have just one. But they look something along these lines. Really quickly, determine is that exo or endothermic? Good. How do I know it's exo? Good. Lower than higher. Right. So the end, this always represents products. This always represents reactants. What do the two hills in it represent? Yeah, it's a multi-step reaction. If we had a mechanism to go along with this, you would see the two parts, which kind of will connect us when we get into Unit 5. But in terms of exo and endo, that's the biggest thing, is high to low. And an experiment type thing, so if they describe a reaction, I have a beaker, and there's a reaction. If the beaker gets colder, or meaning the temperature goes down, is that endo or exo? Good. So temperature going down in a reaction is endothermic. Sometimes people mix this up because that means the thermometer, right? Because that's like the surrounding part of it. The system is taking the heat away from it. The reaction is using the heat that's available, hence it goes downward, and then vice versa. In terms of values, we have delta H. So delta H officially is called enthalpy. That's its official name, or change in enthalpy. The change in enthalpy for endo is what sign? Good. So good to link like those things together. Positive delta H means endothermic, and then negative means exothermic. Once again, showing the direction that it's going. Honestly, in this unit, the whole idea is finding delta H, but in like 3 possible ways. So the first possible way to find delta H is through calorimetry, which is experiment. Right? You literally do the reaction, you measure the temperature change. What's the equation that goes with calorimetry? Yeah. So anytime you read a question that talks about or uses the word calorimetry, or like we put this in a calorimeter, think this, because if it's FRQ, you're going to use this equation guaranteed. If it's multiple choice, you're probably going to at least think about this equation, maybe not do the detailed math of it, but anytime, always link those two things together. Now, with calorimetry, what's the connection between Q and delta H? Or how do I get to delta H from Q? Good, so delta H is Q of the reaction over the moles of the reaction. Now what we mean by the moles of the reaction is its limiting amount. So if they give you multiple things, you have to figure which one is going to run out first, because once it runs out, then the reaction stops. And that's the one that goes on the bottom. So it's not total, don't mix that up, because the mass up here is total, but the moles is just what is limiting based on the balanced equation. And then the Q of the reaction is seen from this, except, do you remember what happens to it?
The sign flip.
The sign flip, yeah. The way to think about it is because going back over here, if temperature goes down, delta T would be positive or negative. It's always final minus initial, so it would be negative, which would make Q negative. But we know delta H needs to be is positive when it's endothermic, and so it's always a sign flip. I just always make sure that the logic of this makes sense. When you're writing delta H, if it's F or Q, it's almost always a point for the sign. So if you're finding delta H after you get the number, pause for a second and think, okay, does this sign make sense? Is it an endothermic process? Okay, then it should be positive. Right, that to me keeps it from like mixing yourself up. But questions on calorimetry? Once again, the setup for calorimetry is literally styrofoam cups. And that's it, right? That's a calorimeter. Obviously there's fancier ones, but it's just something that insulates heat with a thermometer in it so I can measure the temperature change. So, pretty simple reaction. So, okay, the second way that you can find delta H is from just already calculated data, and those are, two of them are on your formula sheet, one of them is not. So another way you can calculate delta H is the product minus reactant equation. So this is very simple form. This one's on your formula sheet. This one uses delta H's of formation. So that's kind of how you know you're going to use that equation, is the delta H will have a little f by it, and the problem will give you a table of delta HFs. And then it's just products minus reactants. The other delta H equation that also comes with a data table, so the problem would have a little table, is bond energy, where they'll give you, hey, an O to O single bond is this much energy, and an O to O double bond is this much energy. The trickier part, so this one's not on your formula sheet, so if you haven't made note of that, it's just what breaks, what's formed, so it's fairly simple, but definitely something to review. The thing about this is you kind of have to draw Lewis structures to use this equation, because you have to know what type of bonds are in the structures. If they don't, sometimes I've seen a problem where they'll give you Lewis structures, and then you can just count up like how many single bonds, C to H bonds, or whatever there are. But any questions on those two equations? Hopefully those are ringing a bell. But yeah.
So if it's like a triple bond, would you consider that one bond or three bonds?
3 bonds. So they would have a different energy. Yes, like on the data table, it would have something like N to N, I'm just making up numbers here, is like 150 kilojoules. But like N to triple bond N is like 360 kilojoules. So yeah, so you wouldn't like do this one times 3, you would just take that value. If you would times it by a value if you have multiple of them, by like 3 of these things. But yeah, great question. Any other questions on those two equations? Okay, and then the third way you can find delta H is through Hess's law. I hope your brain remember Hess's law was the day where I came up with a really weird quiz question that you all thought I was trying to trick you about like driving to Costco and then back to Walmart. I can't remember my question because I made it up. Remember that time where it's like, oh, my house is here, I drew a house on the board, Costco's here, I drove here, but then I went back, and how many miles did I drive, right? And I'm kind of remembering that silly question.
Yeah.
Okay, so Hess's law is the idea of if I have multiple equations and I know their heat, I can relate that to an unknown equation by manipulating them in some way.
Oh, is that like the flippy one?
Yes. So like, all right, let's see if I can come up with the right example here. So like, if I have an equation of like A plus B becoming C, and its delta H, we're just gonna do easy numbers here, is 20. And then, sorry, making up chemistry questions is the easiest thing. And then let's say I have E plus F also equals C. Okay, and the delta H for that equation is 50. And then the equation I want to know the heat for is A plus B becoming E plus F. So this like the unknown. So what would I need to do to figure out it's delta H?
You flip the middle one, so then it's -30.
Yeah, so this would flip because I need those to be products, which also is convenient because C, we want to go away because it's not in this overall reaction. And then since it flipped, it flips the sign. And then you just add. The other thing you can do with Hess's law is you can also multiply. So in case I needed more A's or something, you can times this by 2. Let's say, once again, like if it was like this type thing, then I could times this whole equation by 2, which would then times the heat by 2 as well. So, questions on Hess's law? Hess's law is, the name itself is specific to heat, but this idea of taking equations to make another equation is something, a theme spread throughout all of chemistry. So that's something like, look at this as like a really big picture, that if a problem gives you multiple equations, and then asks you about another equation, think along these same lines of like, all right, I just need to rearrange things, so that when the equations add up, and then whatever I did to these is gonna change those, and then I can add them, so. Yeah, pretty much if you think of unit 6 as delta H, like that's all unit 6 is, but there's 3 ways, kind of 4 ways, because there's 2 equations here. But there's 4 ways I can get to delta H, like that's the entire unit. But it kind of simplifies it, but. Any other general questions that have come up about thermodynamics before we go to our next topic? Okay. Oh, shoot, Trevor, we might need to have you slide over.
Oh.
I totally forgot that I was filming. I'm gonna double check it. It's fine. They actually probably could still see. Well, now they can see it, so it's okay. Okay.
Good old Trevor.
I'm glad I realized it now and not like an hour and a half later, right? Okay, so thermodynamics.
No assistance in the class. The one seat.
Okay, so stoichiometry. Jake, you're the one who requested this. You want just like an overview of like, oh, okay, like how do I know when I read a question that stoichiometry is the pathway I want to go?
Yeah.
Okay. So stoichiometry is, the way I think about it is it's just unit conversions. That's what stoichiometry is. It has a fancy name in chemistry, but it's used once again in all sciences. It's simple as asking the question of like, well, how many inches are in 20 feet? Like that is stoichiometry. So one way that you know you're going to be using stoichiometry is the unit that it's dealing with. One big one that I'd always, is kind of like, I wouldn't say it's like a guaranteed stoichiometry, but most likely is grams. If you're finding a gram unit or the mole unit, those are generally stoichiometry things because of molar mass, gram to mole relationship. The only other equation that really has moles in it is like Herfnert, but then you would kind of know because it's also going to give you pressure and volume things. Another way you really know you need stoichiometry is almost the lack of values. Like if they're not giving you that many numbers to work with, meaning you can't plug them into one of our formulas, it's most likely because you're just going to use stoichiometry and using like the values that we have. So let's kind of review really quick everything that connects. So with stoichiometry, moles is the center. When in doubt, mole it out. Okay, if you come to a problem and you're like, okay, I need to get to this unit, I have this unit, get to moles because moles connects to everything. So let's just review what connects to the mole because maybe that will help a little bit. So the first one is moles connects to grams through what relationship?
Molar
Yeah, so molar mass, that's periodic table, adding up values. Once again, just a side note, if it's a multiple choice question and I'm finding molar mass, drop all decimals. Round your numbers, make them simple, because you don't need to be that specific and it'll just waste your time to like, so So I just like, I would look at hydrogen, call it 1, lithium, I call it 7, sodium 23, like round them to the nearest whole number and use that because it'll make it a lot faster. Okay, moles can connect to, honestly, this one's pretty rare, but we'll bring it up just as a review, like in AP Chem, but it can connect to particles, which could represent atoms, molecules, ions, like getting down very, very molecular wise. And you remember what connects particles and moles? Very good, yeah, so that's our Avogadro's number, 6.02 times 10 to the 23rd, which is on your formula sheet. It's in one of the side columns, like when it's defining variables. But just know in case, once again, on test day, your brain's like, oh, I need Avogadro's number, and then you're like, wait, is it 3.6 or 6 point, you know, isn't there reference to that? It's just in the very top atomic structure, as Avogadro's number off the side there. So just, you know, if you haven't noticed that. But once again, I don't even know if you've seen, like, it's just pretty rare because we normally just keep these in moles, but just, that is one too. Moles can connect to liters of a solution.
Of course, but it's never actually liters, it's always in milliliters, so you have to convert the milliliters to liters, which is always stupid because I always forget.
You forget that one of all
Well,
these.
no, I
Really,
just,
Austin?
it's just hard to
Oh,
do it, I don't know, it always takes like twice as long as it should.
Austin.
I don't forget it, I just,
So what
This is
connects
like the
those two
Texas
pieces?
number.
I know.
So we actually have
22.4.
2 liter relationships. So there's liters of a solution and then liters of a gas.
Oh.
So yeah, so this one is for 1 mole of gas, it always equals 22.4 liters
At STP.
at standard temperature and pressure.
Man, this is, I do.
It's on here too. Yeah, it's in the bottom, if you go to the gases section, bottom, very bottom, on the defined variables, it's kind of in a weird way, but recognize it as 22.4 liter per mole, where it says ideal gas. Yep, you don't have to memorize it. But keep in mind that's if it's a gas situation, and you have to be at STP too. So if they're giving you pressure and they're giving you temperature, this won't work. Because if it was at standard temperature and pressure, they would just say that, and then that would work. But yeah.
Yeah, but it's not a standard temperature, do you unique with an RT?
Yeah, so then you'd be using Perfner for sure.
Okay.
Yeah, no, great connections. I guess we could almost do another one of like liters of gas, not at standard, and then it's Perfner is your connection between them. So what connects this?
Molarity or density?
There you go, yeah, so molarity. Yeah, so molarity is the main, because molarity is moles per liter. And that formula actually is also on your formula sheet. It says, once again, I don't know why they wrote some of them, it's in that same section of gases, liquids, and solids, and they wrote it as a sentence. Not like an equation. I know, I'm like, what? Yeah. But it like tells you what it is, it says molarity M equals moles of solute per liter of solution. But once again, I don't know why. Sometimes that throws students off because they just, as glancing through it, they don't see an equation, but recognize molarity is there for you, forget what it is, so.
That's just silly of them.
It is very silly. Once again, like, why did they do that? I don't know. Okay, let me think. Other connections. Oh, Sophia, question.
Like if I ask them like to calculate like the volume of like this one is needed to make similar with the other solution, like how do you do that?
Like, are you talking about like diluting
Yeah, like-
something technically?
Yeah, like if something's like the volume of 0.1 molar needed to make 50 milliliters of 0.5 molar.
Okay, so just diluting it. So there's a few, the biggest thing to recognize, so with a dilution is you have a container, you know its molarity, and then you typically are gonna add water to decrease its molarity. The significance is the moles aren't changing, because you're not adding anything except water. So there's 2 ways you can think about it. One is you can just think along those lines that the moles aren't changing, and so you find the moles of what you have, and then compare that to the new volume. So you like get out of molarity and then go back into molarity.
Like this is the volume means like the volume of the, like not a volume of water, like the volume of the.
Yes, how much of the concentrated one do I need to use to keep the moles the same? There is another equation we did talk about that's not on your formula sheet if you want to memorize it. It pretty much just does the stoichiometry just in one step versus like go to moles and go to concentration. It's the M1V1 equals M2V2 equation. If that one rings a bell or not. But
Okay.
this, it's an easy one to memorize because it kind of has a pattern to it. But that will do it all for you though, Sophia. But if you were to forget it, you can just remember what dilution means. You can also do it that way too. But one other one that I can think of right now is moles can always connect to moles, meaning of one thing to something else if you have the reaction or the balanced equation. So that's a big thing with stoichiometry is that they give you a balanced equation and they say, hey, I have 10 grams of this, how much of this can I make? Right, get to moles of the one thing, then you can get to moles of the other, and then pretty much all these branches exist on that side too. So, any other questions about stoichiometry as I ponder if there's anything else?
How do you know when to use like stoichiometry versus like what we did in Unit 1?
Unit 1 is stoichiometry still.
Oh.
Yep. Yeah, and really stoichiometry we've done, here's another one I thought of that, like all year long. It's just the idea, honestly the moles is kind of the theme, but it's just the idea of like, all right, let's connect this to this. The difference is in Unit 1, we didn't cross this bridge yet, and we just stayed within one side. So kind of the way to know is if the question says, hey, I have 20 grams of CO2, how many moles is that? Meaning I'm not changing substances, then you know you're not crossing the mole bridge. Versus, hey, I have 20 grams of CO2, how much water would it make in the combustion reaction or something like that. So kind of pay attention to like, does the substance change or is the substance staying the same? That makes sense.
Can you combust CO2?
Like, if 20 grams of CO2
Yeah, you said it would,
produce,
right, it's like.
Okay.
how
CO2
much
is
water
water.
also
Would it be assuming that like the other thing it's combining with is in excess?
Yes, yeah, no, great question, or
Why not?
clarification that, yeah, if, so there's always multiple things reacting, right? Yeah, so unless if it doesn't specify an explicit amount, assume excess. Another one I thought of that moles connects to, which we just left from, is it connects to kilojoules. So what connects kilojoules and moles?
Joules.
Entropy, well,
There you go, fix it there. Delta
wrong
H.
word. Delta H.
So once you have delta H, because delta H is literally kilojoules per mole, you can then convert other things. So that's a big thing is if you've already found delta H, like on an FRQ question obviously, or if they give you delta H, and then they ask you about like changing something, like, hey, what if we now used 20 grams instead of the original? You can then just go grams to moles, moles to kilojoules, because you now have that unit given to you. So,
So is delta H always in kilojoules per mole?
yep, always.
Okay, so in MCAT, the Q represents joules, though, not kilojoules.
Yes.
So that's the conversion you have to make before that.
Yeah, great clarification, Jake, because I didn't mention that before. Yeah, so you always convert joules into kilojoules when you go to delta H. And they'll always, the next thing is even though delta H, so that's another one I guess we could write over here that's not on our list. So the delta H of kilojoules per mole, like this isn't on your formula sheet, but every question I've ever seen that they ask you to find it, they like describe the units. So they say, hey, find the enthalpy of the reaction in kilojoules per mole. So it like kind of gives you the equation, like the molarity sentence, but just as a sentence in the question. So,
Yeah, that was in our last FRQ, like they gave us a chart and it said the change of H number and then next to the number it said kilojoules per mole.
perfect, yeah. So pay attention to the units that are given, because that can also give you an equation if it's not explicitly stated on the sheet. Yeah.
So
So wait, I just thought of something. If you're like doing a question and it like gives you a point for units, if you just put a random number with units, will you still get a point?
I think so. So yeah, so if you know, once again, not every question gives points for units,
Yeah.
but that is a good reminder to always put units, because there are some that have it. But yeah, if you got the number wrong, but you have the correct unit to go with it,
Or the correct sign. like-
or sometimes the correct sign, you can still get points. Yep, definitely. Yeah. Tricky thing, you just don't know which question it will be, but that's why I always put units, and don't be afraid, like if you're running short on time and you're like, well, I know what the units of this should be, I'm gonna write an answer and put a unit with it, yeah, maybe you'll scout a point of it, so. Did that help Jake a little bit with stoichiometry?
Yeah, that was amazing.
Okay, any other stoic questions for now? Yeah, go ahead. Trying to think really quick if I can think of any other things that moles can connect to, but.
Oh, it's actually on the formula sheet right here. It's delta G is the moles related to Faraday's constant, standard reduction potential, or the volts of E.
That's true, so I guess eventually moles can go to, I wouldn't
If
call
you,
that,
if you already know delta G and already know the volt.
the other
volts,
ones, then you can connect that one too,
um,
so. Okay, good, can I erase? Oh, that black marker's made my board dirty.
Okay, can we go over, like graphs and different kinds of tests that can like pop up in the,
You want me to skip to graphs real quick? Before you have to jet out? Yeah, this is a big question, so I don't know if I'm gonna be able to hit everything, so if there's, cause there's lots of different types of graphs you can see, right?
I had a review video on that.
review video on it.
Like, they just went over every single type of graph
So
that you
maybe
can.
one, I mean, we can still do some here, Joel, but if that's something that's like been getting to ya, then so watch that one.
potential and.
Yeah, so there's so many, I don't even know where to start. Different graphs you could see. As with any graph, right, the first thing is always paying attention to your axes, right? What is my x-axis and y-axis telling me? Because that in a sense will then guide you on how to read the graph and what information is given.
All equal.
One graph that often confuses students are distribution graphs. We did one of these in one of the periods last week for like when we were doing our bonus question theme, of like,
Oh.
it's not the best drawing thing, but something. The thing about distribution graphs is, for those that are familiar with integrals, you read them as the area under the curve, is one good way to look at it. The entire shaded space, so typically this side represents the amount. But you should look at it as like that whole area is the amount of molecules, which is why when temperature goes up, number one, it changes the speed so they get faster, but that's why it scrunches down, is because if it just like stayed the same height, right, then you'd be widening the area. That makes sense. So I'm gonna draw in red like an incorrect graph. So like if I were to keep this but go as high, right, that area is way bigger than that. Yes, they're moving faster, but that can't be the graph because you can't get more molecules just because you're moving faster. So that's why number one, why we see this distribution. It's also that when things speed up, they get spread in that you still have some molecules going slow, but now you just have some really going a lot faster and the overall average is shifted. But just kind of keep that in mind with those graphs. But so typically the farther out the one is the faster it's going, right? Also a greater distribution is coming throughout. Other big graphs, we'll bring in absorption. That was a good one. So absorption graphs, or what absorption is it's typically, let me think of my axes really quick. So like normally this is absorption, and then this is concentration, meaning molarity. These two things should be linear. graphs, what we'll see is like something like this. I mean, at least they'd love to do questions like this type idea. And then talk about the possible errors that could have happened with this measurement, because it should be linear. So let's review really quick. Does anyone remember what absorption is measuring? So this is like, I brought in the device. It was like a little rectangular box, and I apologize, we never had to do a lab on one of these. And then it had like a tiny little plastic rectangular thing called a cuvette.
Oh, which
Is the fancy name of it. And it just like, I can go grab it real quick, but you just like set the cuvette inside, and then what happens?
Like you like use it at like different like wavelengths and like sometimes it'll like have more absorbed and sometimes less depending on what kind of light it is.
Yes, I was looking for my phone to shine a flashlight, but I left it back there. But yeah, like it's literally like shining a flashlight through something, and then detecting on the other side how much light passes through. But you can be very particular with the flashlight you are shining, meaning of a very specific wavelength on the other side. So that's all. When you see absorption in a question, just the sample, flashlight, what's going through. Now, what would be the general connection? So pretend these paper clips are molecules. Okay, so this right now I would say is a very high molarity solution. So what's the connection between absorption and molarity?
The higher the molarity, the more it absorbs.
Yeah, or the less that would pass through, right? So higher concentrated things don't let a lot of light through, just like if I were to shine a light through a lot of paper clips, right? Not as much would pass through versus if I had less. So we always see not only a linear relationship, but it's also always a positive slope because of that connection of higher concentration means more absorption. Because absorption means less transmittance. It's the opposite of what's passing through. But
So what are all like the possible errors again?
so, one big one, is the cuvette. You have to be so careful with cleaning, so you clean it before you put it in. Because otherwise, if you have fingerprints on it, so let's think about what type of error that would cause. So if I got this dirty with my hands, and then I tried to measure, is that going to create more or less absorption? Point up or down?
More.
So more or less absorption if my cuvette is dirty. Good, yeah, because it's gonna block the light, right? So that's a possible error as it talks about not cleaning the cuvette correctly. A big one is preparing your molarities correctly, meaning if this is supposed to be, don't mind my scale here. Well, let's say this is supposed to be 3 molar, but instead I accidentally didn't dry out the thing, so it had extra water in it, so it's actually now like less than 3 molar. So if the molarity is less than what I think it is,
How about absorption?
there'd be less absorption, so that would probably go to the dot. Other errors, let me think. Those are really the big ones. Another thing you can use this graph for is also filling in, so that you kind of create this calibration curve, because then you can measure anything, a random sample, get this, and find its polarity. So we used to do this in college. We used to measure, we'd go and gather water samples from the rivers in Cedar City. And then, so you create a calibration curve, because then you can take your unknown water sample, which you have no idea what its concentration is, just scoop it out of the river, right? Run it through this, it will give you this value, and then we can say, oh, the iron concentration today is this polarity. So that's kind of another, like, I've seen that a lot on multiple choice questions where they'll give you a graph, they'll give you the absorption of some unknown, and then you find the piece there. So, other questions that come to mind about absorption?
How would you get like a mass percent from that? Like if say it was saying like you dissolve this into this to get a certain concentration,
Yeah.
and then like how would you know the mass percent? I think I kind of just explained it to myself.
I think you did too. So,
You didn't explain it to me.
okay, so working back from that, Joel, so if they told you, or you're saying they don't tell us how much they put in.
They tell us how much they put in.
So they say, throwing out numbers, so they put 5 grams in 100 milliliters. What was the question asked?
Well, or it's more like, they don't tell you how much they put in, they're trying to figure out how much was in the certain sample, like you were just saying earlier.
Oh, okay, so you'd be able to get, from this graph, you'd be able to get its molarity, and then from the molarity, you should have how much of the original sample you
Convert
got.
it to moles from.
Like, yeah, like I scooped up a liter of it, so then you can go to moles and then to grams. That's how I would think, because I'm visualizing your question perfectly.
It's just a leader.
Well, it's like the ones that are like, what's the mass percent of iron in this thingy? Do you just like go to moles and then see, wait,
So mass percent, you gotta eventually get to grams, right?
okay.
So you go 2 moles, so from molarity, if you have a volume, you can get to moles, and then you can always go to grams with periodic table, right? And then you have to somehow have the original amount to compare to, because percent is part over whole. So that would, I assume, be given to you, they'd have to say this is how much the original sample was. That is a good review thing, kind of side note that grant brings up, is like percentage. There's a lot of different ways they can ask you a percent in chemistry, but keep in mind a percent is all the same concept of a part over a whole. So we have problems that talk about mass percent. We have problems that have percent ionization. And none of these are on your formula sheet, but a percent is just, okay, find the percent of that thing that they're talking, oh, here's another one, percent yield. I guess I should add these to our list down here if you wanted to have them. But it's just find whatever the thing they're focused on, that's the top of your percent, over the total, and then times by 100. So all percents, just like your percent on a test, is how many you got right, over how many you could've got right, times by 100. But, yeah. Oh wait, no, I had another. Oh, so there is an equation on your formula sheet that does deal with absorption. It's Beer's law is the name of it. Once again, it doesn't
It's the
really matter.
alphabet.
It's the alphabet one, so A, oh, that's not A.
Delta equals ABC.
So capital A equals little ABC. It is on your formula sheet, but if particularly like a key word that you're gonna use this equation that I look for is path length. That's very unique to this equation. Cause that's something that would always be given. That's like the size of the cuvette. Like, is it a half inch or what size of, what is the light passing through? So it's rarely something they'll have you find, cause it's like, you just know it from what you're using. So if they give you that, that should be a big hint to use this equation. C is, once again, all the variables are defined, but C is concentration. A is the molar absorptivity, which is also something that will most likely be given, cause it's like a unique constant for the solution. So depending on what solution you're measuring. And then A is absorption. Big A is absorption. So this is like, this equation is how like, this can sometimes like also be like created from. So, have you guys even seen that, have you seen that equation yet on any of the practice tests?
No.
It's like a rare one, like every few years, there's one question. You use it.
We had an absorbance question on the 2019, but we didn't use it.
But didn't use the equation. So, but it's a good one just to like, once again, in your head, kind of keyword here, right? Or if you see the word absorption and it feels mathematical, like free response, pull that equation out, and then it's pretty simple to use, so.
You didn't do
Yeah.
This isn't like super important to us taking the test, but those things that shine a light through, are they like really, really accurate? Like if it was like a super, super low concentration, could it still, like is there a point where it's not it doesn't work?
Yeah, so one of the big things with using the device is finding what light maximizes the absorption. So super old school ones that I used in college, you literally would test every wavelength from like 400 to 900. And then you would, so you'd like set the device to 400, measure. Set it to 401, measure. 402, to
Why
measure.
not do it the way that it was like, set it at 400 instead of 900 to figure out which one's closer, then cut it in half and then do.
Yeah, I mean, you kind of would find the best like area, but what you did is you would create, nowadays ours, like the ones I have for you guys, will do this like automatically, will create a calibration. So before you get this, so another graph I guess that you could possibly see is what's called the absorption graph. So it's like connected to it where this is absorption down here.
All right, teachers and staff, Shanna Omer is going to teach us how to cook some Star Wars salad. If you want to make your way down to the foods room.
Go!
You can sign up, that's okay, she's got extra, so head on down.
What do you guys think
That's
about
what this
birthdays?
word, that's what the birthday is?
So,
It's alright, they were
The
doing
secret's
yoga.
unveiled.
If you were at like 9, they said they were doing yoga,
so
so.
they do, on these teacher work days, they have like scattered throughout the day, like random little like break things you can go participate in if you want to.
It's a teacher party day.
So there's like a meditation moment this morning you can go to. And then if you want to for lunch, you can go to a cooking class for like your lunch break. So that's what it is, but I'm obviously not going, so. Okay,
It's a party
so
day.
with this graph, what you would get is it has something like, oh no wait, I did that backwards. Absorption is still Y. Sorry. So wavelength here, and then absorption here, and then what happens is you get something like this, and then that tells you what wavelength to run your calibration program to help maximize it. Because otherwise, if you try to run your calibration at this one, it wouldn't work very well. So yeah, great question. Any other questions about absorption graphs or absorption in general? Any other graph ones that are in your brain right now, Joel, that you,
I think that was the main one.
is that the main one that kind of helps a little bit? Okay. And that's good to know, so maybe, yeah, for your next review video, watch the graph one.
Yeah.
So there's like the, it's a catalyst graph where it's like, I think it's kind of more to do with catalyst than it is actual graph. It's like, for one of the testings we had, it's like, show how it is with a catalyst. And
Oh, yeah.
I thought catalyst would always break it up into multiple steps, but apparently it was still just one step.
So, it was an FRQ, and if I, was it FRQ? Yeah, so honestly, I think, I talked to somebody about this, I don't know who. So yeah, so if I'm remembering the question, like the original graph was something like this, right? And then the question said, draw the effects of the catalyst, right? The biggest thing is catalyst will lower activation energy, start and end do not change. But the hill does, so I think the answer key is something like this, right?
Yeah.
Right? I think though, and it wasn't explicit on the answer key, but without anything telling you otherwise, it could totally also be that.
So
That's a lot.
I think you got it, yeah, I talked to someone about it, and I told them to give it to, I would give it to you, because the only reason, because yeah, a lot of times catalysts do add extra steps. I think it's just, this is like more advanced of an answer than you're looking for. But I don't think it's wrong.
Yeah, I definitely.
The only reason like that could be wrong is if they explicitly show you the mechanism with the catalyst and it didn't break up into steps.
Yeah.
But they didn't show that, so, yeah. No, great clarification there.
So it's just in general, it lowers the activation.
Yeah, that is the definition of what catalysts do, is catalysts lower activation energy by doing multiple steps or something else to make that happen. So, can I erase this? Everyone good here? Okay, that kind of leads us into Unit 5 of kinetics. So Unit 5 I kind of try to think about in similar to Unit 6, where, so Unit 6 was just find delta H. You can find it this way, or this way. Unit 6, the overarching theme is find a rate law. That's it. What color should we use? So that's really what Unit 6 is find a rate law. Now there's 3 ways, I think 3, that you can find a rate law. First off, what is a rate law?
It's how fast do we actually
Rate
proceed?
equals K and then other stuff.
Okay, so it's always written like, if the problem says, what is the rate law? Keep in mind, it's an equation, right? It's a whole equation that shows what influences the speed. So it's not rate law equals, sorry, it's just rate equals. So this is a rate law.
Rate law equals rate equals.
So rate equals lowercase k, not capital K. They're two very different things. Okay, just known as the rate constant. And it is constant for a reaction, but it's not always constant. So you'll have to find it somehow. So rate equals K times the concentration of, actually I'm gonna change it this way, not A, let's say reactant A. Oh, I did not spell reactant very good. I'm just gonna keep going. Okay, to some power, and then you would continue on for every reactant. Products are never in rate loss. Don't mix that up, because a lot of people with equilibrium start doing product over reactant for this. Two totally different things.
So do rate laws not work for equilibrium reactions, because there's the both forward and backward?
They do, because you can still have, in a sense, a rate for an equilibrium reaction, but the definition of equilibrium is that the rate of the forward and the reverse are equal.
Oh, I get
So
it.
once you write it for the front, in a sense, it's also for the reverse.
Unless
And I
it's
guess
not in
technically you could write, so this would be like the forward rate law. It's not wrong to write the rate law for the reverse, and then do it based on the products grant. I guess the big thing is you wouldn't ever combine products and reactants in the
Yeah.
same rate law. So yeah, great question. So with this rate law, concentration, once again, polarity, to the power, and these are the orders. How we say that a reactant is 0, first, or second order. Those are the main three, but keep in mind everything, there's others in between. You'll never have to find one of those, but remember the one that we had on that test that confused some people? They could tell it to you. So we had a test one time where it said that the rate order for hydrogen was 3, or something like that, and a lot of people were like, oh, well, 3 doesn't exist, so that must be like the overall order, and thought it needed to add up to 3. But the test was just telling you, no, put 3 above H.
Yeah, that was a weird
That
day. I
ring a
remember
bell?
that one.
Yeah, that was annoying.
I think it was the test for Unified is where that question came out. But, so keep that in mind that you can have half orders. Orders can be a fraction, they can be bigger than
Austin, you're
2.
not allowed to call yourself.
But the only one you guys have to find
Well, no,
from
I'm
data
just
is
talking
0, 1,
about
or 2.
situation.
Okay, so let's talk about the ways to find this. So the first way you find a rate law, once again, the way you find it, similar to delta H, is just dependent upon what the problem gives you. So one thing they can give you is they can just give you, I'm gonna just call it experimental data table. Okay, this one should be pretty obvious in what they give you, so the table obviously can vary, but the key parts of information would be something like this. Okay, where we have, let's say it's a reaction of A and B. Okay, it's like trial 1, 2, 3. Okay, and then it has the measured rate. Just ringing
These
a bell.
ones are so nice. I like these ones.
Okay, so they say like, this is 1, 1,
1, 2.
1, 2, 2, 1, something like that.
Oh, and that's to figure out the order, cause like.
Yeah, so then let's say the rate, I'm just gonna be real, normally they're like to exponents, right? So it's like 1 times 10 to the negative 2 polarity per second, 1 times 10 to the negative 2 polarity per second.
1 and 2. Negative 4.
No, it should just be 2 times 10 to the negative 2.
Let's just go,
2 times.
yeah. sometimes like, once again, just giving you an example, there are enough numbers. So if they give you a table like this is a matter of you just compare and see how did changing this substance change the speed of the reaction. So this is where we say, all right, well, from trial 1 to trial 2, A didn't change. I doubled B, but the rate stayed constant. So B must be
Zero.
zero order. Yep. And then I could compare 1, 2, 3, because now B didn't change. I doubled A and the rate doubled, so that makes A first order. Yeah.
So, what is zero order? Zero order is when it doesn't change, even if you're seeing.
Yes. Keep in mind with this chart, so this is what we control, and then this is the result. So I chose to double it, but the result was no change, which means it has no effect, so it must be zero. So zero order is the reaction, didn't change even though I put more B inside. So, any follow-up questions with those data tables? Have we seen any of these on any of the practice so far? Not the most recent ones. Okay, it's not one that's always there.
Is A first order?
Yeah, so first order is same change, and then second order is double, quadruple, or it can be, like this tripled and this 9-tupled.
So it's basically just a
Just
square.
square, because think of that's where it goes up here, is the 2 goes as a square.
And if it's cubed,
So that's why we don't do triple order things, because then it,
you get some hairy numbers very fast.
yeah, the numbers get crazy, so. Good on that? Okay, the second way in which you can find a rate plot is from graphed data. Or I will also say they sometimes don't show you graphs, but they do just show you a table of data. This one is like pretty guaranteed that there's gonna be at least one multiple choice question, at least, that is about the different types of graph. So this is the one where if it's as a table, it would have like the concentration of A. It has the natural log of A, and then 1 over A.
If you want an example, it's question 13 on the first practice test.
Perfect. Does everyone kind of know what I'm talking about here?
So whenever it's in the brackets, it just means concentration, so in the rate law, it's concentration to the
Yes. Yep.
Okay, that's one.
No, that's a great connection. Brackets always mean molarity. That is the universal sign in chemistry, in science, to say molarity.
Doesn't parentheses mean like the gas, right? The partial pressure?
Parentheses are definitely more like, yeah, like, cause that's why we don't typically measure pressure in molarity, so. But I'd say it's, parentheses aren't as like all, cause they could just be used as like mathematical
Yeah,
parentheses,
it's-
but yes,
It's
definitely.
used as, parentheses are used because it indicates multiplication.
Yeah.
So then, natural log of A is first order, right?
Yeah, so the big thing here is what are we looking for with our graph or our data? Linear. Yeah. So we're looking for which relation, it's always versus time are the graphs, but you're looking for which relationship is linear. So like Sophia said, if this one is linear, it's a first order. You'll only do it for one substance at a time, by the way. Because you can't tell, like, so it'd only be for A's order. You can't find A and B's without a whole nother set of information for B, by the way. Good, so this would be first order. If it's this one, it's zero order, and then second order. And once again, you're looking for the linear, if it's a number. Once again, linear meaning you add the same number every time, right? Or they would actually show you graphs, and then you just pick, which would always be time versus something, and then you look for of the 3 graphs, which one is linear. A little bit easier if they just make the graphs for you, but sometimes they do, sometimes they don't. Questions on that? Now there is kind there a word for that?
Dex-
Negative exponential?
Yeah, just,
I figured dexponential. I'm going with that one.
Yeah, it's
So if they only show you this graph, and it's perfectly, look how perfect that was,
If there's half-life,
Exponential.
which connects to half-life. So first slice, the reason why this graph exists is first order reactions have a consistent change across time, meaning they always cut in half. There's an equation for half-life on your formula sheet. G of 1/2 equals 0.693 over K, which is the K in here. But it only applies to first order reactions. So I would definitely make like another trigger in my brain if I read a problem and it uses the word half-life. I would also think, okay, think first order, because it probably is like a first order reaction, and then so that's another way, is if you're given this graph, you can actually claim 2 of the 3. Actually, you could pick all 3 orders. Because 0 has to be linear, first order has to be this, and so second order is neither. Right? So if it's not linear and it's not exponential, it has to be second order. So actually, you could claim from one graph, if it's concentration versus time, what order it is. And it's just a thought that popped in my head. Other questions?
How do we find the rate constant?
Oh, great question, Kate. So coming back, so it kind of depends once again on what method is used. If this method is used, once you have the orders, right, because I can find the orders from this, you then just pick any trial, plug in the concentrations, plug in the rate, and solve for K-math. If it's this method, if it's first order, and you have that, you can use this equation. So once again, if they give you half-life, you can find K or vice versa. If they don't give it to you, the slope of the line is K. So whichever one is linear, the slope is always K. So you just would have to find the slope of the line. So just using like, once again, this one, it's pretty rare with this method to find K, because finding a slope by hand off a graph isn't the most accurate thing to do. But you just do like y minus y over x minus x. But you could, so. And then, yeah, those are 2 ways so far that we find K. And then the third way to get a rate law, which you wouldn't actually be able to find K from, because you don't have any data. And remember the third way?
mechanism.
A mechanism. Okay, can I erase this? I kind of wanted it all at once, but.
And mechanisms are always hypothetical, right? Because they can't be proven or something like that? Or?
They eventually can somewhat be proven, I guess, but they're definitely like a proposal thing. Like, okay, based off what we know and what we can measure, we're gonna, I guess, they can't ever 100% be guaranteed, so yeah, but you can like with
You can find evidence.
evidence, yeah, and so then be like, well, this one supports it, and until otherwise, we're gonna say it's it. But a mechanism, so mechanism's the third way. Mechanism, once again, threading themes throughout. Similar idea to Hess's law. Of this idea of, I have these parts, I have these equations, I want this third equation, how can they manipulate to become it? But in terms of the end goal is not to get the overall, it's to get the rate law from it. So mechanism, once again, it's gonna look familiar, so we have A plus B becoming C. And let's say, well, let's go here. And then let's go
C
C plus D becoming yeah, that's fine.
You have A plus D plus B.
And then with a mechanism, they'll pretty much always give you what the overall reaction goal is. So the overall reaction goal is to have A plus B plus D becoming E. And then the other big thing with mechanisms is which one is called the rate determining step, or nicknamed.
Which one's slower?
The slow step, right? Which they will show you in the problem because that is determined experimentally. You can't know just by looking at things. So let's say, for example, we say that this is the slow step and this is the fast step. They'll also give you the rate for each step. So we can say, all right, well, let's pretend the rate for this step is KB, and then let's say the rate for this step is KD to the second order.
Well, wouldn't the overall just be the first rate because it's the slow one?
Good. So when the slow step is first, it is the overall. Because once it happens, then the reaction just zooms to the end, so the rate of this doesn't matter. So good. So when the slow step is first, it is the overall. So this would be the answer.
Wait, where does it see that one?
So then if the slow step is second, thank you. What am I doing? Okay, I'm trying to think of my made-up problem here.
You'd have to do is K, D, concentration of D, concentration of C,
Okay, there we go.
and then plug it.
Okay, so if the slow step is second, what you have to check for is that there aren't any what in the rate.
Products.
True, but there shouldn't be any to begin with. Intermediates. So intermediates should not be in a rate law because they're created and used. So this can't be my final answer. So you have to substitute in something that is equivalent to that intermediate. Now when the slow step is second, what else will we also see on the fast step? Yep, it's an equilibrium always. If the fast step is first, it's always an intermediate because, or sorry, equilibrium because it's like waiting for the slow person to finish. And then it can go, but it like doesn't sit still, right? So it's going, so C equals A and B, so the overall would be substituting in A and B for C. We'd have K, D2, A, B. And that would be the final answer. Is that ringing a bell? So, there have been a few problems. It doesn't happen super often, but sometimes this one was pretty clean that C equaled A and B. But let's, once again, just go in here. If like F was here,
Uh-oh.
there's one problem I've seen it before where you just have to divide F to the other side. Is you have to isolate C by itself. And so actually the overall rate law would be this. Does that, think of it just mathematically, does that make sense mathematically speaking? If AB equals C, F, we're getting C by itself. Not super often, but
you just minus it because of plusing and not minus?
No, it's a concentration. So
technically
it's saying
order of
as the
operations,
concentration of
it's the
F
same.
increases, the concentration of C.
Either way you would write it. Okay, questions on mechanisms?
I remember the mistake.
Yeah, I wish there was a better word.
If there's anything else I can think of.
Plusing and minus.
Should we count these as our review video notes?
If we're taking them. No, because it counts as your study group. But,
Yeah, what if we,
you already did 3 before today?
Well, I can't do two of them.
Well, you can do extra for extra credit.
Wait, I can actually pass with an A?
I'll let you do this, let someone do this the other direction. You can use one of these for a video. If you've already gotten 3 study groups and you do an extra and you wanna use that in place of a video, that's fine, go with that. 'Cause someone asked the opposite, they
Wait,
use
but
one
aren't
video.
are videos more points than study sessions or the other way?
Technically videos are weighted a little more because they're quizzes,
Okay. and
but
what
I
are
will,
these?
like, you could submit these notes in place, if you took notes today.
Oh,
Does
so
that
what
make
if I did like 3 videos, except one of them was for last time because I forgot to write it.
Yeah, what if we forgot to submit like study session or video? We're just like, and now it's already
Jamie,
closed.
we do we just forget.
We're just so worried about cramming in study times that we forget.
Well,
that
there's
we're
other
supposed
ones,
to
because
turn
there's
them
gonna be
in.
multiple, so just on the next one, submit two.
Okay,
Because you're just
okay.
like, oh, I'm done, and then you forget.
And then, yeah, because I was too busy taking notes, just
So
like.
yeah, so on the
that's
new
what
one
they
that
wanna
is
do.
opened up for this study group, just submit 2 things.
Okay.
Doesn't the dean need a 2 in front of it to make it a second order, right?
Yeah,
Oh, I'm so
yeah,
glad
I
you
was
guys-
complaining about it the whole time to Daniel, he's like, oh, it's fine, she just decided, and I'm like, no, it's not.
Okay, but I do wanna emphasize this with rate laws. In an overall, the orders have nothing to do with coefficients in an overall reaction. There can be a 2 here and not a 2 there in an overall reaction. Now you are right, for a stepwise mechanism, they are elementary, so it should match exactly. But do not confuse, like if they give you a balanced equation, let me erase all this. Some of you are looking at you, very big eyes. Okay, so this is not a mechanism anymore. Okay, this is just the overall reaction. Okay? Say that down. You cannot say by just looking at that, oh, second order, first order. Can't do it. It might be that, but coefficients do not determine orders. You have to have data in a graph, in a chart, or a mechanism. So,
So some mechanisms, how do you find it?
by doing the substitution.
Okay.
Yeah, the steps of the mechanism would always be given to you, or if they tell you, so if they tell you that it's a step, or the other word is elementary, if they tell you this, then yes, the rate would actually be rate equals K, A to B. But only if you know it's a step. So they'd have to like explicitly say. But most of the time they give them to you if it is a step. So, good clarification. Thank you. Okay, anything else with kinetics? Okay, now we're talking about catalyst and the graphs, that's the other part of this. Oh, the other thing that we didn't really mention, it's a little more like makes sense, but knowing what things can you do to a reaction to speed it up? Like what can I do in a lab setting to make a reaction typically go faster?
Or catalyst and
So a catalyst, good.
change the temperature.
Heat, so at the molecular level, why does heat make a reaction go faster?
Because
It makes the
how
particles
fast they're hitting all
go.
the things.
Good, that's a big thing, remember with FRQ questions, when they're talking about justifying and they use the word molecular view, that's like a big thing to make sure you pay
So
attention
you
to.
can draw a picture.
You could draw a picture, but make sure that your discussion is at the molecular view. Otherwise, you could be somewhat right, but not. It's another great example of remembering to get to the whys when you justify. You can't just make the statement of temperature makes reactions go faster. That's a statement, that's not a why. So be careful with statements when you need to justify. You can write that, but then you have to say, why does that happen? Sometimes we're prone to just like throwing out facts that we know, but you don't get points for facts very often. So, other things, so catalyst temperature, pressure if they're gases. So keep in mind, pressure doesn't influence liquids or solids. But yeah, pressure is a great one, because that would, once again, bring the molecules closer together, causing more collisions. One more I can think of. Volume, which is kind of pressure, because, but yeah, kind of on the same notes. Oh, I have 2 actually listed.
The concentration of it.
Concentration. Now this is where you have to be cautious. if I have a 1 molar solution, and I pour in more 1 molar solution,
It's 2 more.
it's still 1 molar. Okay, so to
Addition's not
increase
working.
concentration, you have to literally add more moles. Meaning either more solid, or get rid of water, right? But keep in mind that sometimes students say amount, but just because you pour more in, doesn't make the concentration go up, right? Okay, I have one more.
State of like the reaction.
Good, yeah, or a lot of times I think of like the surface area of it, right? It's like when I did my flamethrower thing, where like you can spread the substance out, it can react a lot faster. Once again, it's all about number of collisions. If there's a question about how do we get more collisions, or how, not, they don't typically say that, they'll say, how can you speed up this reaction? Your brain should think, okay, how can I get more collisions? Because more collisions make it go faster.
You should do the flamethrower one again, cause I forgot about it.
Just because we need
Yeah.
to.
You're right.
Can we incorporate flamethrowers onto the AP?
Yeah, so that's what we mean by surface area. It's not a catalyst because it's a reactant, you need the oxygen, but by increasing the area, the oxygen can react with the particles. Versus like I had in that little pile, remember?
I'm
The
struggling as it
oxygen can
is.
only react with
I'm
like.
sorry about that we can do that and it still makes sense. Others of us need to stick to the basics.
Yes, yeah, so temperature will affect both. It will make them move faster, which gives you harder collisions, and you also have more collisions. Okay, any other questions that have come to mind? Kinetics? Okay, we're going pretty good with our list, but we are about 10 more minutes. Okay,
I think for this one, you need to stand up and like act out the shape.
should we do Vesper yoga?
Yeah.
Since I did miss my morning yoga session. Okay. This is definitely like for the sheets, it's good to review and stuff, but it definitely is like, it's kind of one of the ones that is more memorization. To me, it helps if you visualize them, it helps with the memorizing, because their names are logical to how they look. So if you get to see what it looks like in real space, right, that can help. How do you want to do this? Want me to just like draw shapes and just practice things? I'm just gonna do them as like, oh, I'm buying this.
I don't remember what it looks like.
Do you want me to draw them as what you would see as a language structure, probably? That's what you'd see on your paper. Okay. I'm just gonna do A's and B's for simplicity. This is this. This is this. Name of this sheet. Once again, the more you can visualize it, like it makes sense why that's called linear, right? Yeah. Okay, good, I saw a lot of you see 3, so you knew it was trigonal something, and then planar means
It's all on one plane.
right, bond equal.
One.
So in real life, it looks.
Oh, cause it's like 360.
Yeah, so this is a resonant structure for sure, because the double bond could be here, or it could be there, but it's all equally distributed.
But the double bond doesn't.
Good. Yeah, double bond doesn't change the shape, it doesn't really change polarity, it changes the bond length, like the bond's shorter and stronger, but in terms of like all the Vesper stuff, not really. Yeah, count it as one thing. Oh, hybridization, right? It's still, double bonds still count as just one thing.
So it is like one of the, like where like the bond switches, right?
Resonate.
And when it's resonant structure, does it make it less stable or no?
The idea of resonance is it's helping it be more stable because it's equalizing it throughout.
Is it less stable than if they were all just like a single bond? Right, it's like different molecules of a single bond.
I don't know. I'll have to learn that one later. That's a good question. I don't think so.
everybody, a lot of people did double bond in all of them.
Yeah.
Like, how do we know when it was to do that, or like, two double bonds, one single bond?
That was a weird one to me, because to me, that was the only right answer.
Also, like, how does the octet rule work with the,
So everything that is bigger than, so phosphorus and bigger can expand their octets in the central.
Okay.
Outside atoms will never have an expanded octet. So if you draw a picture and you have an outside one with more than 8, you've done something wrong. And then if it's anything smaller, it cannot do an expanded octet.
So phosphorus and what?
Yeah, so most can, but like, if you have carbon, nitrogen, or oxygen in the middle, do not give them an expanded octet, because it's definitely wrong, so. Yeah, does that help a little bit? Okay.
So for a resonance structure, what if it was like C with the double bond and then B had the single bonds? Would that also be resonant or no?
Oh, so no, if it's a different element, I mean, it depends on the element, it may not resonate.
Okay,
Particularly like if this is hydrogen,
yeah.
right, a double bond's not gonna resonate to hydrogen. So yeah, you can have double bonds that don't resonate if it's not the same substance.
Okay.
So, let's do another one as we're going through this. What hybridization would this have? This one?
SP2.
Okay, let's throw another structure up here.
But it's bent.
Mickey Mouse.
Yeah, so it's bent.
And it's SP.
And the bond angle is less than 120, because it's the same as this, but a ghost pushes them a little closer together. Hybridization. Still SP2, yeah.
Whoa.
Because lone pairs still count as a domain, so it's still 1, 2, 3 domains. So. Okay, more pictures.
Ow.
Elf.
Tetrahedral.
Tetrahedral, this one, bond angle.
That's it.
Oh, 9.5.
Yeah.
Actually, that is a good question. How do you remember that?
One less than all the bonds. That's like, it's like that was, yes.
Yes, the way I think about it is the letters add up to the total number of domains. So this has 1, 2, 3 domains, so 1, 2, 3 is the way I think of it. But yes, it will always be the P is 1 less, because you always have the S. That kind of right. Yeah. I didn't know what I just said.
Is yours fine? Okay. Yes, it's fine.
Yes. Only lone pairs on the center is all we care about for shape, for bond angle, for hybridization. These ones should have them, right? Balance when you're drawing your picture. But yeah, outside of that, they're too far away to affect it. Hybridization? Aiden, your question.
If you have like just A and B, would it be S?
No. Well, this is more than what you need to know. Sometimes orbitals don't hybridize, so they just stay the way they are. It'd actually probably still be an SP, because it's taking an orbital from one and from the other and making the bond.
So H2 would still be SP?
Well, no, because H only has S's, so it's really just, it doesn't hybridize. So it's a little tricky when it's only 2 things, because sometimes they don't need to hybridize.
Okay,
Do you think they'd show us that in the question?
You really don't need to know.
It's where you're merging the
But
different
yeah, the
shells.
idea is when, because it's like, it goes to configurations, how we have like 1s2, 2s2, that when things bond, those orbitals, like the simple way in which we draw bonding is like, here's an atom, here's an atom, they bonded.
Oh.
But what really happens is that these 2 things merge into a new type of orbital, which we call the hybrid orbital. So instead of being an s orbital or being a p orbital, it becomes an sp orbital. So scientists just name the babies by taking the 2 parents and name them.
Gotcha, okay.
That kind of makes sense. Like a baby is a hybrid of the parents. And an orbital is just the two things becoming this new one, but the name they gave it is just the letters it came from. So this orbital is created from S and two P's. So we take one S, two P's, create this new thing. Oh, great question, Abby.
Like, could that?
So once upon a time they thought yes, that the d orbital also hybridized. But then I don't understand well enough to really know. They did more research and then I'm not so sure if it does.
The orbital, all the electrons just go and do its way in the d orbital.
It's like when I was in college, I learned about an sp3d2 orbital.
Awesome.
But now we say, wait, we don't know if that's a d. So this is the highest hybrid you guys want to answer. Okay, oh, I brought something. Okay, name?
So it either does or doesn't. We don't know if it doesn't. Not say that it does, so it doesn't, because you can do all the other things. So
Yeah.
it doesn't, it's not that we don't know, it's just it doesn't until proven otherwise.
Ghost on top.
Is it still like less than one?
Yeah, once you know this, the variants are always just a less than version of it. And like how this was just less than that.
No.
Okay? So less than 109.5. Hybridization. Notice that doesn't change. You have your post.
Are these usually overcome? So we don't know what it is. We don't know what it is.
Yeah, yeah, for sure. The thing is, they could ask you name bond angle hybridization, which would be 3. But yes, never is going to be like, they never really have just
Get out.
So when you come to it, you can't remember, take your best guess. And there's normally, I think we've seen maybe like one
Oh wait, I
each
got it.
test we've taken.
And it was like,
I do remember.
like off.
Yeah, like it's not,
And now this one sits up here.
it's definitely not something we spend tons of time on, right? Because once again, yeah, it's like maybe 1 of 50 points.
That's
It's gonna be
Kansas.
But, you know, 1 point is the difference, so review it, but don't stress it. Okay, and then we have this one.
Super button.
No, this one's, isn't this one linear?
It's like mega bend.
Hyperbend.
So this is the trickiest Lewis structure that deceives people because it looks very linear. But if you place 4 things as far away from each other as possible, they don't do this. They do this, right? And so then if 2 of those sides become ghost, the other 2 sides that are left are bent. And then I heard some of you say the bond angle is going to be less of that. So
It's
less than
less
is
than
the way
less
the book puts it.
Wait, actually, for reals?
Yeah, I didn't think so.
That's stupid.
Because it's just a comparison of it's like.
Hybridization?
SP3.
Yeah, there's 4 of those.
Those are the main ones.
Silly guy.
Have you even seen any of the other ones show up on any of the practice you've done?
No, I've seen like just the dragon.
There's like, I know there's like 1 bond angle question I've seen, like 1 hybridization question, 1 main one. So we do have like all the expanded octet ones too. I don't know if it's worth the time, because these are the more likely ones you'd see. I can see them like using the word, but then like the question based on something else.
That's key.
I got this.
Pretty sure.
Those would be, I guess, if you have these down really good, and you want to do the others, but if you don't have these ones down, get these ones down first.
Oh, I'll probably remember him.
Any follow-up questions on Casper? That we have on the board?
That's what I did.
If you've been here the whole time, it counts as 3, right? Because we've been here an hour and a half.
Wait, actually?
Yeah, because you only need 30 minutes for a study session.
Wait, so I'm
So does that mean I've done 3 hours of study session?
Elias, can we count?
Yeah, so anything
study
past
session
3
or no? Because there
is
are only
extra.
2 of us.
What did you do, Trevor?
I think it would count.
Abby, sorry we didn't talk about bonds.
Five.
Okay, yeah, let me know what follow-up questions you
I
have.
technically done 6, cause I did an hour and a half.
I hope my battery lasts, or I hope that, not like I don't have any internet.
Half an hour, and then I did a half an hour.
No, it's.